You may have been taught that gravity is a force that pulls everything downward. And honestly, that way of understanding it works well enough that you never have to question it, because every time you drop something, it falls exactly as you expect. Everything seems so obvious, so self-evident that there's no reason to doubt it. But if you pause for a moment and ask what is really happening behind that phenomenon, then everything starts to slip away from your familiar intuition in a very interesting way. And what matters here is not to prove you wrong, but to show you that the way you imagine the world may only be a surface layer. Because if you follow this question all the way to the end, you will discover that one of the most basic ideas you've ever believed about reality is actually not true in the way you think. If you want to understand why that view has lasted so long, you have to go back to the work of Isaac Newton, because he was the one who provided the first truly accurate description of gravity. And what's impressive is that he didn't just say that objects attract each other. He also wrote a formula that allows you to calculate exactly how strong that force is in every situation, from an apple falling to the motion of planets around the sun. And if you want to visualize this in the most intuitive way, you can imagine that every object with mass is pulling other objects toward it with an invisible hand reaching through empty space. And honestly, this image works very well because it matches every observation you have in daily life. It's simple, easy to understand, and accurate enough that humans could launch rockets off the Earth and send probes to distant planets just by using that formula. But there is a problem that you will begin to notice when you ask a little deeper. This model doesn't tell you what that invisible hand really is, or how it actually works. And the interesting thing is that even Newton himself was not satisfied with this idea, because he understood very clearly that it is physically very hard to accept that one object can act on another from a distance without any intermediate mechanism. So you have to realize that Newton's formula, no matter how powerful, is still only an extremely accurate description of what happens, not an explanation of the deeper cause. And when you look at the problem that way, the real question begins to emerge very clearly. If there is no invisible hand at all, then what is really happening in this world? And it is precisely at the point where that question becomes impossible to ignore that you need to meet Albert Einstein, because he was the one who completely changed the way we look at gravity, not with complicated equipment, but with a very simple yet extremely profound way of thinking. Let's start with an image you can clearly imagine, a person falling freely from a height. And what matters here is not that you observe from the outside, but that you imagine you are that person. Because when you fall like that, you will not feel your own weight. There is no force pulling you down in the way you once thought. There is no pressure pressing on your body. Everything around you, if there is anything, will float along with you as if gravity had completely disappeared. And this sounds strange because you know very well that gravity is still there, but your experience says the opposite. Now take one more step. Put that person inside a completely sealed box with no windows, no light from outside, and no information about the outside world getting in. The question is, from inside that box, can that person know whether they are falling in a gravitational field or floating freely in deep space? The answer is no, because every experiment that person can perform inside the box gives the same results. Everything floats. Every motion shows no sign of any force existing. And this alone is enough to make you rethink things. But Einstein didn't stop there. He continued with a symmetrical question. What would happen if that box was not falling, but was instead in completely empty space, very far from any source of gravity, and it began to accelerate upward with constant acceleration? And if you were inside that box, you would feel a force pressing you down against the floor, exactly like when you stand on the surface of the earth. Everything you drop would fall to the floor. Water would settle at the bottom, your body would feel heavy, and all these signs would be identical to those of a gravitational field existing. And once again, from inside the box, you would have no way to distinguish between the two situations. One where you are standing still in a gravitational field, and the other where you are in space, and your system is accelerating. And this is not a limitation of the senses or measuring instruments. It is a matter of principle. No local experiment can distinguish between those two cases.
And it is at this point that Einstein realized something extremely important. If two physically completely different situations cannot be distinguished by any local observation, then they are not just similar in appearance. They must share the same deeper nature. And that is exactly what we call the equivalence principle. A principle that says gravity and acceleration are actually the same when you look at them from the right perspective. And this is not a random coincidence, but a fundamental feature of nature.
And if you think about it a little more, you will see that this has very big consequences. Because if gravity is just acceleration viewed in a different way, then there may be no force pulling you down at all. Only the fact that you are moving in a special reference frame. And this begins to shake the entire idea of the invisible hand you are familiar with. Because instead of a mysterious force acting from a distance, what may be happening is something related to the way space and time themselves work. And Einstein went even further by realizing that if acceleration can affect everything inside the system, including light, then gravity must do the same. And that means the path of light can be changed simply by the presence of mass. From there, he began to build a completely new understanding of reality, in which gravity is no longer a force in the traditional sense, but the manifestation of something deeper, something related to the very structure of space and time itself. And if you follow this reasoning to the end, you will realize that we are facing a fundamental change in the way we understand the world, where what you once thought was a force may actually be the result of a geometry you have never seen before. When you reach this point, you begin to realize that what just happened is not a curious coincidence, but an extremely profound principle. Because if you have two physically completely different situations that cannot be distinguished by any experiment you can perform inside the system, then it is no longer a matter of them being similar, but a sign that they are truly the same in nature at a deeper level. And this is exactly what the equivalence principle is telling you, that gravity and acceleration are not only similar in sensation, but are really two different descriptions of the same phenomenon.
And if you accept this seriously, you will be forced to rethink one of the most basic concepts in physics, the concept of force. Because in your familiar understanding, a force is something that acts on an object and changes its motion. But if you are standing on the ground and feel a force pressing you down, while someone else in an accelerating spaceship feels exactly the same thing without any planet nearby, then what you call a force may not be an independent entity, but only the result of being in a specific reference frame.
And this begins to shake the entire idea that there is something invisible pulling objects toward each other from a distance. Because instead of a mysterious force, what may be happening is that you are being forced to move in a certain way by the very structure of space and time. And if you think about it a little more, you will recognize a very interesting paradox. In free fall, where you think you are experiencing the strongest effect of gravity, you actually feel no force at all. You become weightless. Everything around you floats. And that experience is exactly the same as if you were very far from any source of gravity. This is completely contrary to your initial intuition, because you were taught that the stronger the force, the clearer the sensation.
But here it is the opposite. When gravity seems to disappear from your experience, that is precisely when you are moving in the way nature wants you to move. And this forces you to ask again whether gravity is really a force in the way you still think. Because if it were a force, then why can you eliminate the sensation of it simply by changing your state of motion? And why can acceleration create an experience that is completely indistinguishable from gravity without any mass around?
And when you start asking these questions seriously, you will see that the problem is not in the details, but in the foundation. Because your entire understanding of force may be based on an assumption that is not completely correct. And from here, a completely new perspective begins to emerge, in which the motion of objects is no longer explained by pulling or pushing forces, but by them following the most natural paths in a deeper structure of reality. And this begins to lead you to the idea that space and time may not be just a passive stage where everything happens, but that they themselves may be actively involved in determining how everything moves. And when you think in that direction, you will feel a very clear shift in your intuition, because what once seemed obvious is no longer obvious. you begin to realize that what you call force may only be the way you interpret a deeper phenomenon you have not seen directly. And this strangeness is not a sign of a mistake, but a sign that you are getting closer to the true nature of the problem, where everyday intuition is no longer enough to describe the world.
And you must accept that there are aspects of reality that operate according to principles you cannot perceive directly with your senses.
And it is precisely at this point, when the foundation of your intuition begins to collapse, that you are truly ready to step into a new understanding, where gravity is no longer seen as a force pulling objects together, but as a manifestation of the way space and time shape motion. And that opens an even deeper question. If no force is pulling you down, then what is really determining the path you are taking in this universe? If you accept that acceleration and gravity are actually the same in nature, then there is a very powerful consequence that you can hardly avoid.
Anything affected by acceleration must also be affected by gravity in a similar way.
And this includes light, which at first sounds strange because you might think that light has no mass. So there is no reason for it to be pulled like ordinary objects. But remember that we have just left the old understanding of force. So the question is no longer whether light is pulled by a force, but whether light is affected by the structure of space and time.
And to see this more clearly, let's go back to a very simple thought experiment. Imagine you are inside a sealed spaceship with no windows, and the spaceship is accelerating uniformly in one direction. Now you fire a beam of light horizontally across the cabin from one side to the other.
If the spaceship were stationary, the light would travel in a perfectly straight line. But because the spaceship is accelerating, during the time the light travels from one side to the other, the spaceship has moved upward a little. That means from your perspective inside the spaceship, the light does not travel in a straight line, but appears to curve downward. And what is important here is that the light is not actually being pulled down in the sense that a force is acting on it. Its path only looks curved because your reference frame is changing over time. Now go back to the equivalence principle. If you cannot distinguish between an accelerating system and a system at rest in a gravitational field, then the phenomenon you just saw in the accelerating spaceship must also occur in a real gravitational field. This leads to a very strong conclusion. Gravity must bend the path of light, not because it pulls the light like a force, but because it changes the very structure through which the light is traveling. And this was one of Einstein's boldest predictions at the time, because it went completely against classical intuition, where light was thought to always travel in absolutely straight lines.
And what makes this idea special is not only that it is logically sound in theory, but that it could be tested by real observation. And that actually happened when astronomers observed light from stars passing near the sun during a solar eclipse.
They discovered that the positions of the stars appeared shifted from their true positions, exactly as Einstein's theory predicted. And this was not a small error, but strong evidence that light is indeed bent when passing through a strong gravitational field. And when you think about this, you begin to realize that gravity does not only affect objects with mass, but also affects the very way information travels in the universe, because light is the medium that carries information. And if the path of light can be changed, then the image you receive of the world is also changed. And this means that gravity is not only a force phenomenon, but also a profound geometric phenomenon, where space and time determine how everything moves, even things without mass. And when you look at everything this way, you will see that the initial idea of a force pulling objects together becomes insufficient to describe reality, because what is really happening is not a force acting from a distance, but a distortion of the very stage on which all motion takes place.
And light, instead of being an exception, becomes the clearest evidence that we are facing a completely new understanding of gravity, where everything from matter to energy follows rules determined by the structure of space and time.
And when you accept that light, the fastest thing that seems to escape everything, is still affected, then you are getting very close to the biggest leap that Albert Einstein made. Because he did not stop at saying that gravity bends the path of light. He completely changed the way we understand space and time themselves. And this is where everything becomes truly profound. Because in the classical view, space and time are two separate things. Space is where everything exists, and time is what measures change. But Einstein realized that these two cannot be separated like that. They must be combined into a single structure we call space-time. And this is not just a new name for the same old thing, but a completely different way of looking at it. Because in this structure, every event has both a position in space and a position in time. And you cannot change one without affecting the other.
And once you accept that light always travels at a constant speed, you are forced to accept that space and time must adjust to ensure that. And from here, Einstein realized that what we call gravity is actually not a force pulling objects together, but the manifestation of space-time being curved. And to visualize this, you can imagine a stretched flat sheet representing space and time. When you place a heavy object on that sheet, it dents the sheet downward. And if you roll a small marble nearby, it will no longer travel in a straight line, but will curve along the dent. And what is important here is that the marble is not being pulled by an invisible force. It is simply following the most natural path on a curved surface. And this is the core idea Einstein proposed, that mass and energy curve space-time, and objects move along those curves. And when you stand on the ground and feel gravity, you are actually being prevented from following that natural path, because the earth is pushing you upward.
And this explains why in free fall you feel no force at all. Because at that moment you are following a geodesic, that is, the straightest possible path in a curved space. And this may sound abstract, but it explains many things that the old understanding could not explain. For example, why all objects, regardless of mass, fall with the same acceleration in a gravitational field. Because they are not being pulled by a force that depends on mass, but are simply following the same geometric structure. And this also explains why light, even without mass, is still bent, because it is also traveling in space-time just like everything else.
And when you begin to look at the world this way, you will see that the idea of an invisible force becomes unnecessary, because all motion can be explained by the shape of space-time.
And this leads to a very big change in the way you understand reality, because space and time are no longer a passive stage where everything happens. They themselves are active factors that determine how everything moves. And when you think a little deeper, you will realize that this also means that if you change the distribution of mass in the universe, you are not only changing the forces between objects, you are changing the very structure of space and time.
And that means the paths that everything can take also change accordingly. And this is why the orbits of planets, the paths of light, and even the flow of time can all be affected by gravity.
And when you reach this point, you begin to realize that we are no longer talking about force, but about the geometry of reality. And gravity, instead of being a pulling force, becomes the manifestation of how space-time is curved by the presence of mass and energy. And this is not just a different way of phrasing things, but a much deeper understanding, because it not only describes the phenomenon, but also shows you the mechanism behind it.
And when you accept this view, you will see that the world you once thought was simple with pulling and pushing forces is actually far more complex and beautiful, where every motion is the result of the geometric structure of the universe itself.
If you look at everything from a geometric perspective, then nothing is pulling anything. There is no invisible hand reaching from one object to another. Instead, objects are simply moving along the most natural paths in a space that has been curved.
And this may sound counterintuitive because you are used to thinking that if an object changes its direction of motion, there must be a force acting on it. But in a curved space, a straight path no longer looks like the straight line you are familiar with.
And this is the key point you must grasp, because when a planet orbits the sun, it is not being pulled in the sense that a force is holding it there. Instead, it is following a geodesic in a space curved by the mass of the sun. That geodesic looks like a curved orbit to you, but in the space itself, it is the straightest possible path. And when you understand this, you begin to see that the entire concept of gravitational force is just an old interpretation of a deeper geometric phenomenon.
Because instead of saying the sun pulls the earth, you can say that the sun curves space-time around it. and the Earth simply moves according to that structure.
And this is not only true for planets, but for every object, from a stone falling to the ground to light, passing through a strong gravitational field. All of them are following paths determined by the shape of space-time. And this leads to a completely new understanding of gravity, where there is no longer interaction by force in the traditional sense, but only geometric interaction. And you can begin to see this in simple situations. For example, when you stand on the ground and feel your weight, what you are really feeling is not a force pulling you down, but the push from the ground upward. Because if there were no ground, you would be in free fall and feel nothing at all.
And this completely reverses the way you think about your own experience, because the sensation of having a force actually appears when you are prevented from following your natural path in space-time.
And this means that the true force-free state is the state of free fall, not the state of standing still on the ground.
And when you think in that direction, you begin to see that your everyday intuition has been misleading you for a very long time, because it was built on experience in a very special environment where you were always held back by the surface of the Earth. And so you always feel a force that you attribute to gravity, while in reality it is the reaction force from the ground. And when you remove that factor, you finally see the true nature of motion under gravity.
And when you put all of this together, you will see that the idea of a gravitational force is no longer necessary, because everything can be explained consistently by the geometry of space-time. And this is not just a different way of saying things, but a complete change in understanding, because it replaces a dynamical concept with a geometric one. And this has very profound consequences, because it shows that what you once thought were forces are actually just the way you describe a more complex phenomenon using a simpler language. And when you go even further, you will begin to see that many things in physics can be re-understood this way, where phenomena you once assigned to forces are actually consequences of the spatial structure in which they occur. And this opens up a completely new view of reality, where space and time are not just the background, but the determining factors. And gravity is not a force, but the manifestation of how that background is curved. And when you truly understand this, you will realize that your old intuition about gravity is not only not entirely correct, but also obscures a much more beautiful picture, where the universe operates not through invisible pulling and pushing forces, but through subtle geometric laws that govern all motion. In a curved space, straight no longer looks like the straight line you draw on a flat sheet of paper.
Instead, it is the path that an object will naturally follow if there is no force acting on it in the traditional sense. And to see this more clearly, let's start with a very familiar example that you can verify with your own experience.
If you stand on the surface of the Earth and want to go from one point to another by the shortest path, you will not follow a straight line on a flat map, but will follow a curved path on the surface of the sphere. And if you are a long-haul pilot, you will see that the optimal flight paths always look curved on a map, but are actually the straightest paths on the Earth's surface.
And this gives you a very important intuition, that the curvature of space can make natural paths look curved to an observer accustomed to flat geometry. And now bring that intuition into space-time, where the curvature occurs not only in space, but also involves time.
And when an object moves in a gravitational field, it is not being pulled away from a straight line. Instead, it is following its own straight line in a space that has already been curved by the presence of mass and energy. And this is exactly why the orbits of planets look like curved paths around the sun, because they are following geodesics in space-time curved by the sun's mass. And if you look from the classical perspective, you would say there is a force holding them in place. But if you look from the geometric perspective, you will see that there is no force at all. Only the structure of space guiding their motion along the most natural paths. And this also applies to every other object, from a stone falling to the ground to a satellite orbiting a planet. All of them are following their own geodesics. And the interesting thing is that in free fall, you are following a perfect geodesic. That is why you feel no force, because you are not being forced away from your natural path.
On the contrary, When you stand on the ground, you are no longer following a geodesic, because the ground is pushing you off that path. And it is this pushing force that you perceive as your weight.
And when you think a little deeper, you will realize that this explains in a very natural way why all objects, regardless of their mass, fall with the same acceleration in a gravitational field, because they are not being pulled by different forces, but are simply following the same geometric structure. The difference in mass does not change that path. And this is one of the strongest signs that we are talking about geometry rather than force. And when you continue thinking in this direction, you will see that the concept of a geodesic is not just a mathematical tool, but a completely new way of looking at motion, where the question is no longer what force is acting on the object, but what is the structure of the space like? And when you ask the question that way, many phenomena begin to become clearer, because instead of searching for hidden forces,
you are looking directly at the stage where all motion takes place, and understanding how that stage is shaped.
And this also explains why light, even without mass, is still bent when passing near large objects, because light is also following a geodesic in space-time. And if space-time is curved, then the path of light is curved along with it.
And this makes the entire picture consistent, because everything from matter to energy follows the same principle. And when you truly grasp this idea, you begin to see that what you once thought was complex motion is actually just the manifestation of the simplest possible paths in a more complex structure. And this brings a very special beauty to physics, where simplicity does not lie in the external appearance, but in the underlying principle. And the geodesic is a perfect example of that, because it shows that the universe does not need complex invisible forces to control motion. It only needs a suitable geometric structure, and everything will naturally follow its path. And when you reach this point, you will realize that understanding the geodesic is not just understanding a technical concept, but completely changing the way you look at motion.
Because instead of thinking that objects are forced to move in a certain way, you begin to see that they are simply doing the most natural thing possible in a space that has already been shaped.
And that is the key to understanding gravity at a deeper level. Everything you once called motion due to gravity is actually not the result of some pulling force, but the direct consequence of the shape of space-time.
And this means that when an object falls to the ground, when a planet orbits a star, or when light is bent while passing through a strong gravitational field, all these phenomena have the same origin, the geometry of space and time.
And if you accept this, you must completely abandon the idea that there is an invisible force pulling you down, because there is no force in that sense, no pulling rope, no force field in the way you once imagined, only the fact that you are moving in a structure that has already been shaped.
And this becomes clearer when you return to the simplest experience, the state of free fall, where you feel no force at all. And that is not because gravity has disappeared, but because you are fully complying with it. You are following the most natural path that space-time allows. And only when you are prevented from following that path, as when you stand on the ground, do you feel a force. But that force is not gravity. It is the reaction force from the ground.
And this completely reverses your intuition, because what you once thought was the manifestation of gravity is actually the sign that you are resisting it. And when you think deeper, you begin to see that the entire concept of gravitational force in classical physics is just a convenient way of speaking, but not the true essence. It is like an effective model, but not the final truth.
And when you replace that model with the geometry of space-time, you do not just have a different explanation, but a deeper, more consistent view, where all motion is determined by the structure of reality. And this brings a surprising simplicity, because instead of needing a separate force to explain each type of motion, you only need to understand how space and time are curved, and everything will automatically follow. And when you look at planets orbiting the sun this way, you no longer see them being held by a force, but see them sliding along the natural curves of space-time. And this also applies to every other system, from galaxies to elementary particles. All of them are moving along paths determined by geometry, And when you continue in this direction, you will realize that this understanding not only changes the way you explain physical phenomena, but also changes the way you think about reality, because space and time are no longer a passive background, but become the active factor shaping everything.
And this means that when you change the distribution of mass in the universe, you are not only changing the forces between objects, you are changing the very structure in which everything exists. And when that structure changes, the paths that everything can take also change accordingly. And this explains why very large changes in mass can lead to extreme effects, such as black holes, where space-time is curved so much that all paths lead inward.
And when you look at all of this at once, you begin to feel that you are not just learning a new physics theory, but changing your understanding of reality at a fundamental level. Because what was once considered force is now only a manifestation of geometry. And this creates a very special feeling, a shift in perception, where things that once seemed obvious become questionable, and things that once seemed difficult begin to become clearer.
And this change itself is the most important thing. Because when you stop asking what force is pulling this object, and start asking how is space-time curved, you have stepped into a completely different view of the universe.
Where logic no longer lies in direct interactions between objects, but in the structure they all share. And when you stay in that view long enough, you will see that it not only explains things better, but is also more beautiful, because it shows that the complexity of motion can arise from the simplicity of geometry.
And this is one of the most powerful ideas physics has ever produced, because it shows that to understand the world, sometimes you do not need to add more forces or more rules. You only need to change the way you look at what has always been there. At a certain level,
you could say that we have understood gravity in the way Albert Einstein described it, meaning we have in our hands an extremely accurate theory, a set of equations that can predict the motion of planets, the bending of light, the flow of time in different gravitational fields, and many other phenomena with an accuracy that few theories have achieved.
And if you stop here, you might feel that the story is complete, as if we have solved the problem of gravity.
But if you think a little more carefully about what we have just said, you will begin to realize that we have only changed the way we describe it and have not yet truly touched the ultimate essence, because we have moved from saying that gravity is a force to saying that gravity is the curvature of space-time, but that does not answer the deeper question. It only pushes it down to another level. And that question, when asked clearly, becomes extremely powerful. Why does mass curve space-time? What really happens when an object with mass appears and changes the structure of space and time around it? And this is not a vague philosophical question, but a very specific physical one. Because if you say that the motion of all objects is determined by the shape of space-time, then you must explain what determines that shape.
And when you look at Einstein's equations, you will see that they relate energy, mass, and the curvature of space-time in a very precise way. But they do not tell you why that relationship exists. They do not tell you the deeper mechanism.
They only say that if you have an energy distribution like this, then space-time will curve in that way. And this brings you back to a very familiar situation in science, where you have an extremely successful description, but lack a final explanation. And if this sounds familiar, it is because it is very similar to the situation Isaac Newton once faced, when he had a perfect formula for gravitational force, but did not know its real mechanism. And the interesting thing is that we seem to have returned to the same type of question, but at a much deeper level. Because now we are not only asking where the force comes from, but why space and time themselves respond to mass in the way they do. And when you realize this, you begin to see that we are standing at a very special boundary in our understanding, where what we know is extremely accurate, but still incomplete. And this is not a failure, but the way science always works. Because every time you solve one problem, you usually discover a deeper problem hidden behind it. And this is precisely the driving force of scientific progress. And when you look at this question, you will see that it not only concerns gravity, but also touches on the most basic concepts of physics, such as the nature of space, the nature of time, and even the nature of reality itself.
Because if space-time is not a fixed background that can be curved and changed, then the next question is what it is made of, and why it can respond to mass in that way.
And this is where you begin to feel that we are entering a region where everyday intuitions no longer helps much, where new ideas may look very strange, but are necessary to explain what we observe. And what is important here is that you should not rush to find a simple answer, because the history of physics shows that simple answers are often only the first step. And when you dig deeper, you often have to accept completely new views that differ from your initial intuition. And that is why the question of why mass curves space-time is not just a technical detail, but a door leading to a deeper level of understanding, where gravity may not be as fundamental as we once thought, but may be the result of something even deeper. And this prepares for the next step in the journey, where we will have to face even stranger ideas. Ideas that may change not only the way we understand gravity, but also the way we understand the entire universe. And if you have come this far and are still curious, then that is exactly the sign that you are in the right place, where science becomes truly interesting, because it is the unanswered questions that push us forward. When you ask that question seriously, you begin to see more clearly the true position of the theory we are relying on. Because Albert Einstein's general theory of relativity is not just a beautiful idea, but also one of the most successful theories ever built in the history of science. It accurately predicts how planets move, how light is bent when passing near large objects, how time slows down in a strong gravitational field, and even predicts the existence of things no one had thought of before, such as black holes or gravitational waves. And all of this has been verified by observation and experiment with astonishing accuracy, to the point where you could say that if there is any theory we can trust absolutely in its predictive power, it is general relativity. But the problem begins to appear when you ask not what it predicts, but what it explains. Because there is a very important difference you need to recognize, the difference between description and explanation. A theory can describe very accurately what happens without necessarily telling you why it happens. And in the case of general relativity, it gives you a very clear set of rules. If you have a certain distribution of mass and energy, then space-time will curve in a definite way, and objects will move along the corresponding paths. And this works perfectly, but it does not tell you why mass has the ability to curve space-time in the first place. It does not give you a deeper mechanism that explains that relationship.
And this may not matter if you are only interested in prediction. But if you want to understand the nature of reality, then it becomes a very large gap.
And this is not a criticism of the theory, but a feature of it. Because many theories in physics start with description before they can explain. And sometimes it takes decades or even centuries to move from description to deeper understanding. And when you realize this, you will see that we are in a familiar situation, very similar to what happened before when Isaac Newton had a perfect formula for gravitational force, but could not explain its mechanism.
And now we have an even more powerful theory, but we still face a similar question at a deeper level. And this shows you that science does not progress in a straight line, but in layers, each layer providing a new level of understanding, but also opening up new questions.
And in this case, that question is why the structure of space-time responds to mass in the way Einstein's equations describe. And when you begin to think about this question, you will realize that it cannot be answered by general relativity alone, because this theory was not built to answer that question. It was built to describe how gravity works, not its origin. And this forces you to look beyond the scope of the current theory, searching for a deeper theoretical framework that can explain not only how space-time curves, but also why it can curve. And this is where the problem becomes truly interesting, because it leads you to the boundary where general relativity meets other theories of physics, especially quantum mechanics. And when these two worlds meet, contradictions begin to appear, showing that our current picture is still incomplete. And these contradictions themselves are the clearest sign that there is a deeper level of understanding waiting to be discovered. And when you reach this point, you are no longer asking what gravity is in the descriptive sense, but beginning to ask why reality is built in such a way that gravity appears as it does. And that very question will lead you to the next step in the journey, where we will have to face the limits of current theories and begin searching for a new understanding that goes beyond what we already know. Right where you expect unity,
you instead find a profound division in all of modern physics. And to understand that, you must realize that physics today is not a single system, but is built on two great pillars. On one side is general relativity, the theory that describes gravity and the structure of space-time on large scales, from planets and stars to the entire universe.
On the other side is quantum mechanics, the theory that describes the behavior of elementary particles at extremely small scales, where your ordinary intuition almost no longer works. And what is remarkable is that both of these theories are extremely successful within their own domains.
Quantum mechanics gives you predictions so precise that you can measure effects with extremely small deviations, while general relativity accurately predicts how light is bent, how time slows down in a gravitational field, and the existence of phenomena such as black holes or gravitational waves.
And all of this has been verified by observation and experiment. So the problem does not lie in one of the two theories being wrong, but in the fact that when you try to combine them, they do not fit together. And this is precisely the point where everything becomes interesting, because in extreme conditions, such as near the center of a black hole, or in the first moments of the universe, where both gravitational effects and quantum effects are important, these two theories begin to contradict each other.
And when you try to apply the principles of quantum mechanics to gravity in a direct way, the equations begin to behave in ways you cannot control. The quantities you calculate are not only large, but become infinite.
And not infinite in a sense that you can handle with an approximation, but infinite in a sense that the equations completely lose the ability to give finite predictions.
And in physics, when you get a result like that, it is almost always a sign that your model has been pushed beyond the range where it can be applied. And this gives you a very clear message that there is something missing in the way we are understanding the problem.
And that is not a small detail that can be fixed with a refined calculation, but a shortcoming at the fundamental level. And from here, physicists began to realize that we need a new theory, a theory that can combine what is right in quantum mechanics with what is right in general relativity. And that hypothetical theory is called quantum gravity, a theoretical framework in which gravity is described at the quantum level, where space-time is no longer a smooth, continuous background that you can divide infinitely, but may have a deeper microscopic structure. And this idea leads to a series of different approaches, such as string theory, where elementary particles are not points but small vibrating strings, or loop quantum gravity, where space is built from discrete units. And each approach tries to solve the same problem from a different perspective. But so far, we still do not have any theory that can combine all the elements together in a complete way and be confirmed by experiment. And this may surprise you, because we have achieved astonishing scientific accomplishments.
We can measure time so precisely that the time dilation due to gravity must be taken into account in GPS systems. We have detected gravitational waves from black hole collisions, and we can describe the behavior of particles with unprecedented accuracy. But at the deepest level, we are still missing an important piece. And that very piece is directly related to the question we asked from the beginning. Why does mass curve space-time? Because if you rely only on general relativity, you can describe the phenomenon but cannot explain the mechanism. And if you want to go further, you must step into the region where the two great theories intersect, where familiar concepts begin to collapse, and new ideas must be built.
And this is not a step backward, but a natural step forward in science, because every time you encounter such a limit, it is often a sign that you are very close to a breakthrough.
And if we can build a complete quantum gravity theory, it will not only explain why mass curves space-time, but also give us a completely new view of the nature of space, time, and reality. And that will not only change the way we understand gravity, but also changed the way we understand the entire universe. And in the entire universe we know, there is no place more suitable than black holes.
Because these are regions where gravity is not only strong, but also overwhelms every other effect, where mass is compressed into such a small region of space that the structure of space-time is bent to the extreme. And under those conditions, everything you have learned begins to be challenged in the most direct way, because at the edge of a black hole, what we call the event horizon, everything changes in a very fundamental way.
No object, no signal, and especially no light can escape from that region once it has crossed this boundary.
And this is not because there is an invisible force pulling everything back as in the classical understanding, but because space-time has been curved to the point that all possible paths that an object or light can take lead inward. That means no matter which direction you try to go, you are moving deeper into the black hole. And this turns black holes into an extremely important natural laboratory, because here you cannot avoid having to apply both general relativity and quantum mechanics at the same time.
And it is precisely at this intersection that serious problems begin to appear, because general relativity predicts that when matter collapses inward, it can reach a state we call a singularity, where density becomes infinite, and the equations of the theory no longer give you meaningful answers.
And this alone was already a warning sign that the theory was being pushed beyond its range of applicability. But the problem does not stop there, because when you bring quantum mechanics into the picture, everything becomes much more complicated.
Because quantum mechanics says that information about the state of a system is never completely lost. It can be transformed or dispersed, but it cannot disappear. And this is a very basic principle, almost foundational to the way we understand physical processes at the microscopic level.
And now you have a direct contradiction, because if an object falls into a black hole and is eventually compressed into a singularity, then the information about its state seems to be lost, with no way to recover it. And that violates the principle of quantum mechanics.
And when you try to describe this situation with the current mathematical tools, you see that the equations are no longer consistent with each other. They produce contradictory results or lead to infinities that cannot be handled.
And this is not a small detail that you can fix by refining the model, but a clear sign that we are missing an important part in our understanding. Because if your most basic theories cannot all be correct in a real physical situation, then it means that at least part of the picture is incomplete. And this is exactly why black holes have become especially important in theoretical physics. Not because they are rare or strange, but because they force you to confront the limits of current theories in an unavoidable way.
In normal conditions, you can use quantum mechanics or general relativity separately without any problem. But in a black hole, you do not have that choice. You must use both. And this very combination reveals the weaknesses in the way we understand reality.
And when you look deeper into these contradictions, you will see that the heart of the problem is not only about force or geometry, but about information. Because the important question is not only where the matter goes, but how the information about it is handled, whether it is destroyed or encoded in some other form.
And this question has led to a series of new ideas in physics, where information begins to be viewed as a fundamental element on the same level as energy and mass. And when you follow this direction, you begin to realize that gravity may not only be about the geometry of space-time, but also related to the way information is organized and conserved in the universe. And this opens up a completely new view, where black holes are not only extremely strong gravitational objects, but also extremely complex information processing systems.
And when you accept that, you begin to see that what once looked like the collapse of a theory may actually be a sign of a deeper structure waiting to be discovered. Because the history of science shows that every time current theories fail to describe a phenomenon, it is often the moment when a new theory is very close. And in the case of black holes, the contradictions between quantum mechanics and general relativity may be the most important clue we have to build a complete quantum gravity theory. A theory that can not only explain why mass curves space-time, but also explain how space, time, and information are linked together at the deepest level of reality.
And that is why black holes are not only the place where theories collapse, but also the place where new ideas begin to form, where the hardest questions in physics converge and force us to rethink from the foundation.
And if you really want to understand gravity at the deepest level, you cannot avoid going through this region, where all familiar intuitions are challenged, and where simple answers are no longer enough. From these very contradictions, an unexpected turning point appears when Stephen Hawking applied quantum mechanics to the context of black holes in a way that no one had truly done so thoroughly before. And the result he found was not only surprising, but also completely changed the way we think about these objects. Because according to the initial intuition, a black hole is something into which once something has fallen, it can never escape again. No light, no matter, no signal can cross the event horizon to return. But when you consider the quantum effects occurring right at the edge of the black hole, the picture begins to change in a very subtle but profound way.
Because in quantum mechanics, what you call vacuum is actually not completely empty, but always contains small fluctuations, where pairs of particles and antiparticles can appear and then disappear in an extremely short time.
And under normal conditions, these pairs would appear and annihilate each other almost immediately without leaving any observable trace. But near the event horizon of a black hole, the situation becomes importantly different. Because if one of the two particles in the pair falls into the black hole while the other escapes outward, then the mutual annihilation does not occur. And from the perspective of an observer far away, this looks as if the black hole is emitting particles, as if it has temperature and radiation. And this is exactly what we call Hawking radiation, a completely unexpected result, because it goes directly against the idea that black holes are objects that only absorb and do not emit anything.
And this has a very profound consequence, because if a system emits energy, it must lose energy over time. And for a black hole, that means its mass will gradually decrease.
And if you wait long enough, in a time that may be longer than the current age of the universe for large black holes, it can evaporate completely. And this is an extremely powerful idea, because it turns black holes from permanent objects into dynamic systems that can evolve and disappear. But it is right here that the problem becomes more serious, because when you consider the nature of Hawking radiation, you will see that it is almost random. It does not carry detailed information about the state of the objects that fell into the black hole earlier. It only depends on the overall properties of the black hole, such as mass, charge, and angular momentum. And this leads to an unavoidable question. If you have an object with a very specific state falling into the black hole, containing a definite amount of information about its structure, and then the black hole gradually evaporates through Hawking radiation without carrying that information with it,
then where did the original information go?
And if the evaporation process continues until the black hole disappears completely, then it seems that information has disappeared as well. And this directly contradicts one of the most fundamental principles of quantum mechanics, that information is never destroyed.
It can be re-encoded, dispersed, or become extremely difficult to retrieve, but in principle, it still exists. And this contradiction is not a small detail that you can ignore, because it touches the foundation of the way we understand physical processes at the microscopic level.
And if you accept that information can be lost, you will have to change all of quantum mechanics, something most physicists do not want to do because of the level of success of this theory.
But if you keep quantum mechanics unchanged, you must find a way for information to be preserved even during the evaporation of a black hole. And this puts us in a very special situation, where no matter which direction you choose, you are forced to change an important part of the current picture. And when you think deeper about this problem, you will see that it is not only about black holes, but about how information is handled in the universe in general. Because if information can disappear in one case, then you no longer have a principle of information conservation.
And that would affect every field of physics. And this is exactly why this paradox has become one of the most important problems in modern theoretical physics, because it forces you to reconsider the relationship between gravity quantum mechanics, and information. And when you look at the whole picture, you begin to see that black holes are not only extremely strong gravitational objects, but also systems where the most basic principles of nature collide with each other. And it is from these collisions that new ideas begin to emerge, ideas that may lead to a deeper understanding of reality, where gravity is not only the geometry of space-time, but also related to the way information is encoded, stored, and transmitted in the universe.
And when you reach this point, you begin to realize that our original question about why mass creates gravity has led us to a completely unexpected place, where the answer may not lie in mass or force, but in the very informational structure of reality.
And that prepares for the next step in the journey, where we will have to confront the information paradox and its profound consequences directly. In quantum mechanics, there is a principle that is almost inviolable, which says that information is never lost.
Every state of a physical system, no matter how complex, evolves according to laws that are reversible in principle. That means if you know the exact state of the system at one moment, you can, at least in theory, trace back its past or predict its future.
And this is not an arbitrary assumption, but a core part of the way quantum mechanics is built. It is tied to the unitarity of quantum evolution and ensures that no information disappears from the universe. But when you place this principle next to what general relativity predicts about black holes, you encounter a completely different picture. Because in Albert Einstein's description, an object that falls into a black hole and crosses the event horizon becomes separated from the rest of the universe in such a way that no signal can carry its information back. And if that process continues to the singularity, where the equations of the theory become infinite, then the information about that object seems to be erased from the physical picture. And when you add Hawking radiation, which shows that the black hole can evaporate completely over time without carrying detailed information about what has fallen in, you reach a conclusion that seems unavoidable. Information can disappear.
And this puts you in a very awkward situation, because you have two extremely successful theories, each verified by countless experiments and observations. But when you apply them to the same phenomenon, they lead to conclusions that cannot both be true at the same time. And this is precisely the information paradox, one of the deepest problems in modern physics, because it is not a technical error that you can fix by adjusting a few parameters, but a direct contradiction between two pillars of current understanding.
And when you realize this, you must accept that we are facing a real theoretical crisis, where at least part of the picture we believe to be correct must be changed. And for many decades, physicists have debated intensely about how to resolve this problem. Some have proposed that information really is lost and quantum mechanics needs to be modified, while others believe that information must be preserved and general relativity needs to be extended or changed under extreme conditions. And between these two views, many intermediate ideas have been put forward, from information being stored on the event horizon to it being re-encoded in Hawking radiation in very subtle ways that we do not yet fully understand. But what is important is not to choose a specific answer immediately, but to recognize that the very existence of this paradox shows that there is something wrong in the way we are combining our current ideas. Because in a complete theory, contradictions like this should not exist. And this leads you to a deeper thought, that the problem may not lie in each theory individually, but in the way we understand fundamental concepts such as space, time, and information. Because if information is truly a basic component of reality, then the way it interacts with gravity may be completely different from what we are assuming. And when you follow this direction, you begin to see that the answer to the information paradox may not be just a small adjustment in the equations, but a change in the way we understand the structure of the universe, where space and time may not be the ultimate foundation, but emergent phenomena from a deeper layer related to information. And this very idea opens up a completely new direction, where to resolve the contradiction between quantum mechanics and general relativity, you must build a picture in which information, space, and gravity are linked together in a more consistent way. And when you realize that, you begin to see that the information paradox is not only a problem that needs to be solved, but a clue, a sign pointing out that we are standing before a turning point in our understanding of reality, where the answer to the question of why mass creates gravity may lie in the way information is organized at the deepest level of the universe. From this very paradox, a completely new idea begins to emerge. An idea that, if you hear it for the first time, may feel almost impossible to accept, but has the power to solve the problem in a very unexpected way. And that is the holographic principle, a concept that says the information contained in a region of space does not actually reside in the volume of that region, but can be fully encoded on the surface surrounding it. And to visualize this, you can think of a holographic film, where a complete three-dimensional image can be stored on a two-dimensional surface. That means you do not need the entire three-dimensional space to hold the information about the object. You only need a surface with the right structure. And although this is only an analogy, it helps you approach the intuition of this idea, that the reality you experience in 3 dimensions may not be where the information really resides, but that information is encoded on a deeper 2-dimensional structure. And this goes completely against your ordinary intuition, because you always think that more volume means more information can be contained. But the holographic principle says the opposite, that the maximum amount of information a region of space can hold is not proportional to its volume, but to the area of the surface surrounding it. And this idea is not a random speculation, but comes from studying the entropy of black holes, where it was discovered that entropy, a quantity directly related to the amount of information, is proportional to the area of the event horizon rather than the volume inside. And this suggests that all information about what has fallen into the black hole can be encoded on its surface instead of being lost in some singularity.
And if this is correct, it provides a way to resolve the information paradox, because the information does not disappear but is only stored in a way that you cannot directly see. It is spread out on the event horizon and can in some way be re-encoded in Hawking radiation.
And although the detailed mechanism of this process is still a matter of research, the overall idea has changed the way we think about space. Because if information is really stored on the surface, then the interior volume may not be where the fundamental information resides.
And this leads to a very profound conclusion, that the space you experience may not be a fundamental entity, but an emergent phenomenon from a deeper information structure.
And when you think in this direction, you begin to see that the relationship between gravity and information may be much tighter than you once thought. Because if gravity is related to the way information is distributed and encoded,
then understanding gravity may require you to understand how information is organized in the universe.
And this makes the holographic principle one of the boldest ideas in modern physics, because it not only tries to solve a specific paradox, but also proposes a completely new view of reality, where the dimensions you experience may not reflect the true dimensions of the underlying information. And when you accept this possibility, you begin to see that what you once thought was obvious, like space having 3 dimensions and containing information inside it, may only be a manifestation of a deeper structure that you have not directly seen. And this opens a new path to resolving the contradictions we have encountered. Because if you change the way you think about space, you can change the way you understand gravity. And when you go even further, you begin to realize that our original question about why mass curves space-time may not have an answer within the framework of space-time as a fundamental entity, but must be found in a deeper theory where space, time, and information all emerge from a common origin. And that is why the holographic principle is not only a tool for solving the paradox, but also a strong suggestion that the way we understand the universe may need to change at a fundamental level, where space is no longer the stage, but part of a deeper story about information and reality. From the holographic principle, an even bolder step forward appears when physicists realized that the idea of information on the surface is not just a metaphor, but can be written as an exact mathematical equivalence between two completely different types of theories.
And this is exactly what we call ADS/CFT, a result showing that a theory with gravity in a certain space can be completely equivalent to a theory without gravity living on the boundary of that space.
And to understand the intuition of this, you do not need to go into the mathematical details, but only need to grasp the core idea, that the same reality can be described in two completely different ways, one using curved space with gravity, and another that has no gravity at all, but still contains all the information needed to describe every phenomenon occurring in the other space. And this is not just an analogy or an approximation, but a true equivalence, meaning every process in one description has an exact counterpart in the other description. And this is extremely surprising mathematically, because you are saying that two theories that look completely different in structure and concepts are actually two different ways of writing the same physical system.
And if you pause for a moment to think about this, you will see that it is not just a technical result, but a change in the way you understand the relationship between theories.
Because it shows that what you consider reality may not be tied to a single description, but can be represented in multiple different ways, each highlighting a different aspect of the same deeper structure. And this leads to a very powerful consequence, that gravity may not be a fundamental element of nature, but an emergent phenomenon from a theory without gravity at the fundamental level. And if that is true, then the way we ask questions about gravity may need to change completely, because instead of asking where this force comes from or why space-time curves, you must ask what in the deeper theory produces the phenomenon that you interpret as gravity. And when you connect this with the holographic principle, you begin to see a more consistent picture where information on the surface can be enough to build the entire interior space. And ADS/CFT provides a concrete example of how that can happen, where a theory on a two-dimensional boundary can contain all the information needed to describe a three-dimensional space with gravity.
And this is not just a beautiful idea, but also a powerful tool, because it allows physicists to calculate difficult problems in one description by switching to the other description, where the calculations become easier to handle. And this has led to a great deal of progress in understanding complex systems. But more importantly, it suggests that space and gravity may not be things you need to assume from the beginning, but can emerge from a deeper structure related to information and quantum interactions. And when you think in this direction, you begin to see that the space-time you experience may be like a picture that is built up from underlying data rather than a foundation that exists by itself. And this has a very profound consequence for our original question, because if space-time is not fundamental, then mass-curving space-time may not be a basic principle, but a consequence of the way information is organized in the deeper theory.
And this completely changes the way you approach the problem, because you are no longer looking for a mechanism in the familiar three-dimensional space, but must look for a mechanism in a structure that may not have spatial shape in the way you understand. And this may sound abstract, but it fits with what we have already seen, because every advance in physics requires you to abandon part of the old intuition to accept a deeper view. And ADS/CFT is one of those steps where you must accept that two completely different descriptions can both be correct and both be necessary to understand reality. And when you go even further, you begin to see that this does not only apply to one special case, but may be a general principle, that reality can have multiple layers of description, and gravity may be a phenomenon that appears at one particular layer, but does not exist at a deeper layer. And if that is true, then our journey from Newton to Einstein and to here is not only about discovering new laws, but about exploring different layers of reality, where each layer provides a different view of the same world.
And ADS/CFT gives you a glimpse of how those layers can be connected to each other. And that is why it is considered one of the most important discoveries in modern physics, not only for its mathematical power, but because it opens up the possibility that to understand gravity, you may need to go beyond space and time as basic concepts, and that prepares for the next step, where we will begin to consider the possibility that gravity may arise from information itself and from the quantum connections between parts of a system. Gravity may arise from information itself, more specifically from a phenomenon in quantum mechanics called quantum entanglement, a special kind of connection between particles where, when you measure the state of one particle, you immediately know the state of the other, even if they are arbitrarily far apart.
And this is not a signal traveling through space in the ordinary sense, but a relationship already encoded in the joint state of the system. And although entanglement was initially seen as a strange phenomenon that only appears at the microscopic level, where particles interact in ways that classical intuition could not describe, physicists began to realize that when you have a very large number of particles linked in this way, those connections can create an organized structure. And what is remarkable is that this structure can have features similar to the space we experience every day. That means the distance between points in space can be understood as the degree of quantum connection between parts of the system, where parts with stronger entanglement are considered closer to each other, and parts with fewer connections are considered farther apart. And if you follow this logic, you begin to see that space is not a pre-existing background, but can be built from information connections. And this is a complete reversal from the way you usually think, because you are used to considering space as something that exists first with particles inside it. But here, the particles and the connections between them may be what creates space itself. And if space is built that way, then the curvature of space, what we call gravity, may simply be the manifestation of the way these connections are arranged and change over time. That means instead of mass directly curving space-time, as in Albert Einstein's description, it may change the entanglement structure of the system at a deeper level, and that change manifests outwardly as the curvature we observe. And this leads you to a completely new understanding, where gravity is no longer a force or even a basic geometric property, but an emergent phenomenon from the way information is distributed and connected in a large quantum system. And this idea may sound very strange, almost going against all your intuitions about the physical world. But what makes it worth taking seriously is that it is not just a vague speculation, but has mathematical foundations and is supported by results such as AD-SCFT, where the relationship between entanglement and geometry has been shown in a concrete way.
And in those models, you can see that changes in the entanglement structure lead to changes in the shape of space. And this suggests that the two are not independent, but may be two sides of the same phenomenon.
And when you look deeper,
you begin to see that entanglement is not just a detail of quantum mechanics, but may be a fundamental organizing principle of reality, a principle that determines how the parts of a system connect to each other, and thereby determines the structure of the space you experience.
And if that is true, then our original question about why mass curves spacetime can be answered in a completely different way. That mass does not directly curve space, but changes the underlying information structure. And that change manifests as the curvature we observe.
And this opens up a very active area of research in modern physics, where scientists try to build models in which space, time, and gravity emerge from basic information principles.
And these efforts include studying entanglement networks, tensor network models, and many other mathematical structures that can reproduce the properties of curved space from quantum connections. And although we still do not have a complete theory, the progress in this field has shown that this is not only a speculative idea, but a direction with real potential. And when you look at the entire journey from Newton to Einstein, from curved space-time to the holographic principle in AD-SCFT, you begin to see a clear trend that each step forward takes us farther away from the idea of basic forces and closer to a picture in which information plays a central role.
And this not only changes the way we understand gravity, but also changes the way we understand reality in general. Because if information is fundamental, then everything you experience from space to time to matter may be different manifestations of the same deeper information structure. And when you reach this point, you begin to realize that the question of why mass creates gravity may not have an answer in the language you're used to, but needs a new language, where concepts like entanglement, information, and quantum structure play a central role. And that very thing prepares for the next step in the journey, where we will have to confront directly an even more radical possibility.
That not only gravity, but space-time itself may not be a fundamental entity, but an emergent phenomenon from a deeper layer of reality that we have only just begun to explore. When you reach this point and begin to seriously consider the possibility that gravity may be an emergent phenomenon from information, then an almost unavoidable next step in reasoning appears. That if gravity is not fundamental, then perhaps space-time itself is not fundamental either. And this may sound extreme because you have always thought of space and time as the foundation of everything, as the stage on which the universe exists. But the history of physics has shown many times that what seems most fundamental sometimes turns out to be only the result of something deeper.
And to understand the intuition of this, you can think of a very familiar example: temperature. When you touch an object and feel that it is hot or cold, you might think that temperature is a basic property of that object.
But in reality, temperature is not an independent entity, but the result of the random motion of atoms and molecules inside. If you go down to the microscopic level, you will not find temperature as a separate entity, but only particles moving with different energies. And temperature only appears when you describe a large number of particles in a statistical way. And this gives you a very important lesson, that a concept can be very real and useful at one level, but does not exist at a deeper level. And when you apply this way of thinking to space-time, you begin to see that space and time may be like temperature, an emergent phenomenon from a deeper microscopic structure that we have not directly observed. And if that is true, then mass curving space-time may not be a fundamental principle, but a consequence of the way more basic components interact with each other. And this fits with what we have already seen from ideas such as the holographic principle and ADS-CFT, where three-dimensional space can be described by a two-dimensional theory without gravity, and from entanglement models, where the structure of space emerges from quantum connections between parts of a system. And all of this suggests that the space-time you experience may not be the deepest layer of reality, but an intermediate layer, an effective description that appears when you look at a system with a very large number of components. And when you accept this possibility, you begin to see that many previous questions become different, because instead of asking why space curves, you begin to ask what creates space in the first place. And instead of treating time as a basic flow, you may have to view it as a concept that emerges from the change of information in a quantum system. And this is not just a small change, but a complete shift in the way you look at the universe, because it shows that what you experience every day is not the deepest layer of reality, but the result of a complex organizing process.
And this may make you feel disoriented at first. But at the same time, it also opens up a very powerful possibility that if you understand that underlying structure, you can explain not only gravity, but also the existence of space and time itself.
And when you look back at the entire journey from Isaac Newton's gravitational force to Albert Einstein's curved space-time, then to information, holography, and entanglement, you begin to see a clear trend that each step forward takes us farther away from the initial intuitive concepts and closer to a picture in which concepts like force, space, and time are no longer fundamental, but emergent. And if that is true, then the question of why mass creates gravity may not have an answer within the framework of space-time as a fundamental entity, but must be found in a deeper theory where space-time is only a manifestation.
And this completely changes the way you look at the universe, because it turns the universe from a fixed structure into a process being built from the bottom up, where what you see is the result of deeper laws that we have only just begun to understand. You begin to realize something very important.
That although we have come very far in understanding gravity, from Isaac Newton's formulas to Albert Einstein's geometry, and then to deeper ideas about information, holography, and entanglement, we still do not have a final answer to the question of why mass creates gravity. And this is not a failure, but the very nature of science, because a science is not a system that provides absolute and unchanging truths, but a continuous process of building, testing, and replacing models to describe reality more and more accurately.
And every model you have, no matter how successful, is only an approximation of reality, a map, rather than the territory itself. And this is the point that many people often overlook, because when a theory works too well, it is easy to mistake it for the final truth.
But in reality, even the most successful theories have a range of applicability. And outside that range, they may no longer be correct, or may need to be replaced by a deeper understanding. And the history of physics is the clearest proof of this, where each step forward does not erase the old, but places it in a broader context. Newton is still correct in most everyday situations. Einstein expanded that understanding to extreme conditions.
And modern theories continue to go even further. And this gives you a different view of scientific knowledge, not as a series of final answers, but as a series of ever better models.
And in that series, admitting that you do not know is an indispensable part, because if you assume you already know everything, you will no longer have the motivation to explore.
And it is this acceptance of not knowing that keeps science alive, always developing and always ready to change when new evidence appears. And when you return to our original question, why does mass create gravity? You will see that we have gone from a simple answer about force to a more profound understanding of the geometry of space-time, then to even deeper ideas about information and entanglement.
But each of those steps has opened up new questions. And this does not make the journey meaningless, but makes it richer, because it shows that reality has more layers than you thought, and each layer needs its own description, and none of them is final in an absolute sense. And when you accept this, you begin to see that science is not a search for certainty, but an exploration of understanding, where the goal is not to eliminate all doubt, but to understand more clearly what you do not yet know.
And this leads to a very characteristic attitude of balance between confidence and humility. Confidence in what you have verified, and humility before what still lies beyond your understanding. And this very balance allows science to move forward without getting stuck in old assumptions.
And when you look back at the entire journey, you will see that every step forward begins with recognizing the limits of the current model. And instead of seeing that as a weakness, scientists see it as an opportunity to go further.
And this is especially clear in problems like gravity, where the deepest questions still do not have answers. And instead of avoiding them, we use them as motivation to develop new ideas.
And this gives you a very different view of not knowing, not as a deficiency, but as a constituent part of knowledge, an open space where new ideas can emerge.
And if you truly understand this, you will see that not having a final answer does not diminish the value of science, but increases its value, because it keeps the process of discovery always continuing. And it is that process itself, rather than any endpoint, that makes science special. And when you stand here, with everything we have discovered and everything we still do not understand, you can see that what is astonishing is not that we do not yet have a final answer, but that we have been able to go this far in understanding such a complex universe.
And it is this very combination of knowing and not knowing that defines science. Not as a system of answers, but as a journey that never truly ends. The seemingly very simple question of why mass creates gravity makes you realize that you are no longer standing in the same place as when you started. Because you have gone through a long journey from the intuitive understanding that it is a pulling force, to Isaac Newton's accurate but incomplete view, then to the revolutionary leap when Albert Einstein showed that gravity is not a force, but the geometry of space-time. And after that, you continued to be pushed even farther from your initial intuition as ideas about information, the holographic principle, add CFT, and entanglement began to appear, step by step shaking the feeling that space and time are the fixed foundation of reality, and instead suggesting that they may only be emergent phenomena from a deeper layer that we do not yet fully understand. And what is important is not that each step has given you a final answer, but that each step has forced you to change the way you look at the world. Because you no longer ask, what force is pulling this object? But how is space curving? Then what creates space? And finally, what information structure lies beneath all of this? And it is this very shift in the way of asking questions that is the most profound thing, because it shows that understanding is not the accumulation of answers, but the change in the framework you use to understand reality.
And when you look back at that entire journey, you will see that although we still do not have a final answer to the question of why mass creates gravity, we have come much farther than the starting point.
We have gone from a simple description to a network of profound ideas connecting force, geometry, and information. And each layer of understanding opens up a new layer of questions. And this does not make the journey meaningless, but makes it richer, because it shows that reality is not something simple that can be captured by a single answer, but a multi-layered structure that you can only approach gradually. And when you accept that, you begin to see that the goal of science is not to find a final answer and stop, but to continuously improve the way we understand the world.
And in that process, the question is sometimes even more important than the answer, because the right question is what leads you to the next steps forward.
And the question of why mass creates gravity has done exactly that. It has led you from classical mechanics to relativity, then to quantum physics and beyond. And although you do not yet have a final answer, you have a much richer map of reality. And what is astonishing here is not that we still lack an answer, but that we have been able to understand part of this picture. That from simple observations of falling objects, humans could build theories that describe the structure of the universe, predict unseen phenomena, and even ask questions about the nature of space, time, and information.
And this creates a very special feeling, a combination of humility and awe. Humility, because you realize there is still so much you do not know, and awe, because of what you have been able to understand.
And when you stand at this point, you begin to see that science is not a journey to an end point, but a continuous process of exploration, where each answer leads to a new question, and each question opens up a new way of looking at the universe. And that is exactly what makes exploring the world meaningful. Not because you will find a final answer, but because in the process of searching, you gradually understand more deeply about the reality of which you are a part. And perhaps the most important thing you take away from this journey is not a definitive conclusion, but a way of thinking, a way of looking at the world in which you are willing to ask questions, willing to change your perspective, and willing to accept that the deepest things about the universe may always lie just beyond your current reach. But it is precisely continuing to move toward them that makes science special. If you want to continue exploring ideas that change the way we understand the universe, please subscribe to the channel so you don't miss the next videos. See you in the next journey, where we will continue to ask the questions that science is still seeking answers for.